Um, and so and then you learn from this that the expectation value of these guys is proportional to nj, and there's also some U1R phases. So pulling out an overall scaling as the square root of the absolute value of n, you get this, defines this complex vector. This is my direction along which you see my saddle point solution is concentrated. So this is a simple example, maybe slightly misleadingly simple example, as I'll say later, of this idea that if you pick the right, you can kind of engineer the right observables to concentrate you along a direction in a higher rank Coulomb branch. And then,
Philip,
yeah.
Can I ask you a question? Is it obvious that once you compute these correlators for the wrong operators, you can reconstruct those for the good operators? I mean, once you have these correlators for the AI, can you reconstruct easily those for the OI?
So that's a great question. I think, first of all, I'm pulling a fast one by even talking about these things. These are not really well-defined correlation functions. The A's are not not single-valued objects. So I can't just this guy, a product of the AI to the NI, is not a well-defined operator on my Coulomb branch. I have to build something which is something holomorphic in the OIs in the end, or equivalently, is given that they, the relation between the AIs and the OIs satisfy in this, for this example, some polynomial relation. I really should only include not products of AIs, but certain polynomials in the AIs that that manage to be well defined, that are then single valued on the Coulomb branch. So so I've slipped under the rug this this issue. I wrote this because, at least formally, then I can, because locally it just diagonalizes. It's a flat coordinates. Using those as sources, it's easy to write down the saddle point solution. And I just want to use this as motivation that there should exist configurations which can be localized, but to also make them single valued, well-defined operators on the Coulomb branch, I'm going to have to do something a bit more sophisticated than what I've done here. And that's why I said you should really think of them as some kind of not having a single term, but some appropriate set of polynomials in these terms, and then but the idea is that they sort of that they're still you can make them arbitrarily well approximated by a saddle point that still has this still has this form, because they end up picking out this specific direction. I don't know if I said that clearly.
No, I think I understand. Thank you.
So, I mean, basically, I think you're pointing out that I'm not really doing an honest calculation here. So if you put, if you put that in, you get the, this kind of expansion, a kind of an absolute value of n factorial, but really, it's the combinatoric factor is a little bit more complicated, and then an order n piece that depends on normalizations as well as the direction in n space, order n to the 0 pieces from 4 derivative terms, but we still have to worry about these Wess-Zumino terms. And now, again, and this is what I'll spend the rest of the talk talking about, is what can we say about the 4 derivative terms. But one thing that's obvious is once you go to higher rank, instead of there being sort of a unique 4 derivative term that preserves n equals 2 supersymmetry, now because we have many of the different fields, we can potentially write down many different terms which all contribute on our 4 infrared divergences. So they all contribute to, or they kind of are part of the Wess-Zumino term for the axiodilaton. However, granting that we can find a class of observables for which the saddle point solutions are concentrated along a given direction, then it's just a little matter of geometry of figuring out what the axiodilaton field is. What is, if you're at a given point on the Coulomb branch, there's a specific direction, which is the Goldstone boson for the action of that given by the that it points in the direction, that is to say, that it varies by a shift under the action of the spontaneously broken U1R and dilatation symmetries. And then you will then exactly the same argument as in Hellerman and Maeda will then pick off from matching to that Wess-Zumino term a specific log n term, and its coefficient will be set by the anomaly in the same way. So it will just be the difference between the central charge of the CFT at the origin and the central charge at our generic point that we're moving to, which is a U1 squared low energy effective theory. So if we were only interested in the log of absolute value of n contributions, I wanted to say that I wanted to argue here that this can be computed, completely analogously to Hellerman and Maeda for an appropriate class of or a clever choice of operators, and the dependence on sort of the angular directions get hidden in the order and absolute value of n to the 0 and higher pieces. And now, like I said, there are some problems. One is the problem that I already mentioned in response to Domenico's question. The other one is when in my sample calculation, when I wrote down the saddle point, there was some phase in the saddle point solution for each AI, and the phase was arbitrary. This is the U1R phase, and there was nothing, because I did this, I took this isotrivial case in which the 2 derivative effective action is just completely free for the AIs, then there was no way of determining. We know that there's a U1R symmetry, so there's an overall phase of the saddle point, which you can't determine because of the broken U1R symmetry. However, you would expect that that's the only unbroken symmetry, and so you would have expected the relative U1R phases to be determined by something. But at the order of the approximation, the kind of the classical two derivative level, they are completely arbitrary in these isotrivial geometries, just because they're at that level, they're flat, and so they look like a bunch of decoupled free fields, and therefore they actually have an accidental U1 R copies of a U1 global symmetry, one for each of these fields, and so independent phases. So the question is, what determines these? One may be that that these two mistakes in some sense, one is the solution to the other one, that when you put in sources which are actually single valued, that are more like polynomials in the ONs instead of polynomials in the ANs, then or special polynomials in the ANs, that then you have competition between different terms. And so when you find the saddle point solution, depending on the coefficients that you put in those observables, that then fixes for you the relative values of these U1Rs. And you only have to stay at the classical two derivative level, or maybe you have to use fluctuations around this thing, in other words, you'd have to, it's not impossible. I'm just not clear on this point as to whether it may be that the only way to determine these to pick out these relative phases is to also include effects at higher, like four derivative levels, four derivative terms. So maybe I should pause there for questions before I move on to the next thing, which I think I'm going to have to do fairly rapidly. But this was admittedly not a completely solid argument to say that there are a class, to argue that there are a class of these chiral, anti-chiral two-point function observables that can be approximated at large n.
Philip, is isotriviality equivalent to or stronger than or maybe weaker than, what's the relationship between isotriviality and the condition that the infrared couplings don't run? Oh, Philip, I think you're muted for some reason.
Oh, sorry about that. I don't understand why I did that. Yeah, isotriviality means that the low energy couplings are independent of position on the Coulomb branch. Though you have to keep in mind that it's that's basically right. I mean, okay, let me just leave it at that. So I think that's what you mean by saying that they don't run.
Yeah, good, thank you. Okay.
So, and it turns out that that's equivalent to saying that the geometry is flat. It's clear that it implies that the geometry is flat, but the arrow works in the other direction. If the geometry is flat, then it is flat in the special coordinates. That is to say, it is isotrivial. That's a theorem by Dan Fried. Okay. If there are no...
I will ask you later. I'm just since we're done.
Okay, okay. It looks like, yeah, I have 10 minutes left. And so now let's try to go to the order n to the 0 pieces. And for these, we really actually need to get control of at least the 4 derivative terms in the effective action, sort of the next term in the derivative expansion on the Coulomb branch. The 2 derivative terms, right, the superpotential terms in superspace language were the ones that were determined by Seiberg-Witten theory. So assuming that we're just on a pure Coulomb branch, so we don't have extra hypermultiplets and don't have to worry about the existence of massless hypermultiplets, then we can just use a very simple n equals 2 superspace, so a superfield formulation in which we just add in 8 Grassmann variables, and then a chiral superfield with a modulo a slight caveat will then describe a massless vector multiplet. So its bottom component will be the complex scalar, then the gauge enos, and then the gauge field strength. So it's a field, this is the gauge invariant U1 vector multiplet. That is to say, its components are the field strength, not the potential. And so you just expand it out in the usual way. But the field strength satisfies a Bianchi identity. And of course, there are phi cubed and phi to the 4th chiral pieces here, and they are actually related by derivatives to these guys. So these imply that there are extra constraints on this field. So it's actually constrained by some 2nd order differential relation relating A to A bar and its derivatives. So this is kind of the superspace Bianchi identity. Nevertheless, this is an off-shell superfield, so I can just use this to build manifestly n equals 2 invariant actions. And so I can do, I can write D-term actions. Those are integrals of arbitrary functions of my A's and A bars over all of superspace. Each d theta counts for 1/2 of a derivative. So the measure here already tells you it's a 4 derivative, so I shouldn't put any explicit derivatives in the action here. So it's just some function of A's and A bars. And then if you also want it to be U1, scale and U1R invariant, then you can argue on general terms that terms like this can be written as the log of some holomorphic function of the A's times the log of some anti-holomorphic function of the A bars. Okay, where the things inside the logs are homogeneous in dimension, or you can take them if you like to be dimension 1 because you're taking logs of them. So this is just at the level of terms that I can write down. So 4 derivative D terms in a conformal field theory on a Coulomb branch. And however, these terms have some singular behavior at the zeros of the arguments of the logarithms. So that puts constraints. If this is going to be a good term on the Coulomb branch, we should only choose arguments of the logarithms which vanish at the singularities of the Coulomb branch. So what are those singularities? Those singularities come about when charge states become massless. That's places where, and when they become massless, that means they're satisfying the BPS bound. So the BPS bound is given, the mass is given by the absolute value of the so-called central charge of the theory. And the central charge of the theory is basically some integer linear combination of these special coordinates. Really, of the special coordinates and the dual special coordinates, this is the full sort of set of fields which satisfy those Bianchi identities. So are good n equals 2 vector field superfields. And these vectors of integers here, these are elements of the electric and magnetic charge lattice of the theory, and they're quantized by the Dirac quantization condition. And then there's some sublattice of states which become massless at each singularity. And so this suggests that the kind of a general ansatz for the form of these 4 derivative terms could take would be a sum over logs of these integer linear combinations of the special coordinates. So maybe I should say time is short, I'll skip that. So where you sum over charges in the sublattice of states becoming massless at your given singularity. So I is a sum over the different singularities. Q and P you sum over charges in the states becoming massless at that singularity, or arbitrarily light at that singularity. And then you have a bunch of coefficients, and it's kind of at some level, I can just pull this coefficient out, but it's natural to sort of normalize these contributions from the ith singularity in terms of the anomaly coefficient, the difference between the A central charge of the conformal field theory supported on the ith singularity minus the central charge of a free U1. And the idea is just that a term like this, sort of supported, if you want to call it, on this singularity, is going to contain the West-Semino term having to do with spontaneously breaking the accidental conformal invariance of the conformal field theory supported along this singularity, but by moving off it in a transverse direction. But this, of course, doesn't tell us what these coefficients are. And so the question is, how can we, is there a way of actually determining these coefficients a priori, or making and testing some ansatzes, some guesses for them? So here is the guess that seems natural and has some supporting evidence, is that these coefficients are first of all diagonal in Q and P. That is to say, it's the terms that appear are always log Z, log ZQ, log ZQ bar. And that they haven't, and then each of them has an integer multiplicity, which is identified with the multiplicity of massless BPS states. So when I say BPS states, I mean one particle states. So if a set of one particle states is becoming massless, then there are, to any approximation, multi-particle states filling out this whole charge lattice, which are also becoming massless. They're not quite BPS, but there often are, in these conformal field theories, just a finite multiplicity of massless one particle states. And so then you just get a finite, then in this ansatz, you just get a sum over a finite number of terms. And There is some small evidence for this, at least for SUN n equals 4 theories, that that precisely this form for the 4 derivative terms works, in the sense that it matches at weak ultraviolet coupling to a 1 loop calculation. And that was done by, argued by Dine and Gray a long time ago. And for a special class of these isotrivial theories with Gabriel and Mario and Luigi, there's also some evidence kind of along similar lines, or really along these anomaly matching lines, that these things work out for sort of nice simple values of these coefficients. So I'm out of time. Let me just say that there are other, what I want to advocate is that there are possible further checks for that might help us figure out what these coefficients should be. One I've already mentioned is doing engaged conformal field theories. We can do 1 loop perturbation theory and try to match results, or you can try to match to localization results. And there's been some relatively recent work by Beccaria and company on a set of SUN conformal gauge theories, not just n equals 4, but also n equals 2. But I think more generally is, again, by you can try to match this to the result that I talked about in the first part of the talk, by seeing that it gives sort of the correct for this class of angularly localized observables, that it gives that the set of terms, that these set of coefficients in these Wess-Zumino terms, these linear combinations here, then give the correct projection onto the Wess-Zumino term for the associated axiodilaton for moving out in that particular direction on the Coulomb branch. So that's my main suggestion. Even if you had these 4 derivative D terms down, these ones that can contribute to these chiral antichiral correlators, there's also at higher rank 4 derivative F terms that can contribute. They have some specific form. They don't occur at rank 1, but as soon as you go to rank 2 and higher, they could possibly occur. And so you'd also need to understand these terms. And the only thing I have to say here is that these terms are, they're kind of described in terms of an analog of a holomorphic prepotential. It's one that has kind of a 2-index prepotential. And instead of being homogeneous of degree 2, like the prepotential, it's homogeneous of degree 0. But it is holomorphic in the Coulomb, on the Coulomb branch. And so you can imagine the similar sorts of kind of analytic continuation, Seiberg-Witten type tricks that enabled you to pin down, in at least many cases, the superpotential, the 2 derivative terms on the Coulomb branch, may also allow you to kind of to determine these 4 derivative terms. I don't believe anybody has done this yet, but it seems to me that this is a natural and plausibly doable project. So